In the previous video, we talked about barging in with a relatively strong nucleophile to push out the leaving group through an Sn2 mechanism, but now we're going to kindly let the leaving group leave before we even attack through an Sn1 mechanism, which would be, a stepwise process. Having said that, let's get started. We know that the first step is that the leaving group's going to leave on its own. And a few of the principal factors that go into this are, for one, is the leaving group going to be happy about leaving his home, if we might say that. Excuse me, let me erase that. Well, as I draw out the bromine, okay, it has a negative charge, but it's a relatively or larger atom compared to what we see with perhaps oxygen or nitrogen, and it's pretty electronegative, so it can stabilize the charge well enough. It's a good leaving group, like we'd expect with a halogen. And now we have to also consider, is the leaving group going to leave its house or the substrate in a relatively stable position? Is it going to leave the house in good working order? Well, once the leaving group leaves, it creates a carbocation. And if we remember from earlier in the textbook and in earlier sections, that the more neighboring carbon atoms we have, the more stable the carbocation. And this, right here, we're in the best position we can be. We have three neighbors that can donate electron density and help stabilize the positive charge. Now, once the leaving group has left, so we have an open space for our nucleophile to come in and attack. And here, it's the chlorine atom that will come in and attack the position here, which will give us our product through an Sn1 mechanism. A few of the takeaways here when it comes to Sn1 mechanisms are how well the leaving group leaves and stabilizes itself later on. If it's a good leaving group, or even better, that's what we'd want. And also, the carbocation it creates, is it stable or not? Those are really going to be important factors in determining how well an Sn1 mechanism will work. Let's do another problem and see some of the other concepts that go hand in hand with the Sn1 mechanism. And as always, you should be asking yourself before you begin a problem, what are we working with? Well, looking at our starting material, or the molecule we're given, we can see that we have a pretty good candidate for a leaving group, and also that we have some chirality here. So always when you're starting something or looking at a problem, always have stereochemistry in the back of your mind, whether it's possible, whether you start with it, whether you're going to be creating it. And then finally also, we have what we'd expect to act as our nucleophile at some point. It's methanol, so it doesn't have a charge, so we might think that, okay, it's not too strong. And we'll see how that factors in as we go along. So for applying a Sn1 mechanism, first things first, we'll want the leaving group to leave, which will be, once again, this halogen. It's going to be relatively stabilized once it leaves, or I should say, well stabilized. It is iodine after all. I redraw the molecule. Have this positive, the secondary carbocation. Go ahead and draw the halogen over here, stabilized, nice and happy. And once again, as we take another step, we always want to ask, okay, what can happen? Well, here we should notice that, okay, we have a positive charge, a carbocation, next to a tertiary carbon. Well, we know that there's an invisible hydrogen here, or an implied hydrogen. We should expect to see a hydride shift, because if we do that, what's going to happen is, through this carbocation rearrangement, we're going to fill the hole at the secondary carbon and put the hole on a tertiary carbocation, and I'll draw the hydrogen that we moved. So here we actually get a more stable carbocation through a hydride shift, and this would be preferable because we want to make sure that the electrophile we're attacking is available before the nucleophile comes in, because that's a key part of determining the rate of Sn1 mechanisms. So having here our stabilized electrophile, let me go ahead and draw out another one of our nucleophile molecules. The lone pair, is going to come in and attack. So once we do that, we're going to get this. And here I accidentally drew out the methanol as a line in a way, but that's not a problem. Now here, once again, as you adding things, you always want to keep track of things like formal charge, and that's something that we have here. So before we go on, we're wanting a stable product with no neutral. And what's going to happen is, well, if you remember where we had our halogen, it's going to deprotonate what once was the methanol. And the electrons between the oxygen and the hydrogen are going to fall back, and that will take care of the positive charge we observed. So when I draw out our final product, we get this. So now as we look at our final product, one of the initial questions we had was, is there stereochemistry here? Well, is there a chiral center? In this case, there isn't, because these two groups are actually the same. And even if we did create a chiral center, one thing to keep in mind is once you create the carbocation, a carbocation is sp2 hybridized. It has an empty p orbital, so it's flat. We can attack from the top or the bottom. So instead of, in essence, like in Sn2 mechanisms where you see this inversion and stereospecificity, when it comes to Sn1 mechanisms, you should know that we expect a racemic mixture and actually a little more, of the inverted product. In the next video, we're going to look at how factors such as substrate, the strength of a nucleophile, and so on affect Sn1 mechanisms and Sn2 mechanisms, and we'll go ahead and compare them side by side.